Hello dear viewers, I am your friend Shadab Imam and currently we are dealing with the topic of queuing theory under operations research. Today we are going to do some examples on model 1, which is MM1 infinity infinity model. Now, in the previous lecture, we have discussed the details of this model and we have derived some formulas which are very useful. So please watch the previous video first and let us start this video. So before moving on with the problems, let us have a recap of the formulas we require to solve MM1 infinity infinity model. So these are the 10 formulas we need to remember. So let us see one by one. So first formula is probability that exactly n number of customers in the system. So it is given by Pn and it is equal to lambda by mu to the power n multiplied by P0. Now let us see the next formula. It is given as the probability that no customer is in the system. So that means the probability of having zero customer in the system. It is given by 1 minus rho, or we can show as 1 minus lambda by mu. So let us move to the next formula. Probability that the server is busy, or it is also known as utilization factor, and it is represented by rho, and rho is equals to lambda by mu. Now let us move ahead. Probability that the number of customers in the system is greater than capital N. So in order to find this, we need to have lambda and mu, lambda by mu to the power capital N. Now let us move ahead. Average number of customers in the system. It is also known as length of system. So whenever it is talking about system, we will find out length of system. It is given by rho upon 1 minus rho. And if we put rho equals to lambda by mu, we can find this equation in terms of lambda and mu. Now let us move ahead. The next formula is the average number of customers in the queue. It is represented by LQ and it is given by LS, that is length of system, minus rho. Now if we need to find the formula in the form of lambda and mu, we simply will put rho is equals to lambda by mu, and in that manner we can convert our formula in the form of lambda and mu. Now let us move ahead. Average waiting time of customer in the system, and it is given by Ws and it is equal to Ls by lambda, where Ls is the length of system. Now again here, if we need to have this formula in terms of lambda and mu, we can convert it by putting rho equals to lambda by mu in the formula of Ls, that is the formula of length of system. Now let us move ahead. The next is average waiting time of customer in the queue. It is given by WQ and it is equal to LQ by lambda, where LQ is the length of queue. And the next formula is probability that the waiting time in the queue is greater than time t. So it is given by lambda by mu multiplied by e to the power minus of mu minus lambda multiplied by time t. And let us move ahead with the formula. Probability that the waiting time in the system is greater than time t, and it is given by e to the power minus of mu minus lambda multiplied by time t. So these are the 10 formulas we need to remember. Now let us move ahead to the problem. Now the problem here says that customers arrive at a one window drive in a bank according to a Poisson's distribution with mean 10 per hour. Now service time per customer is exponential with mean 5 minutes. The space in front of the window, including that for the serviced car, can accommodate the maximum of 3 cars. Other cars can wait outside the space. Now it has been asked that what is the probability that an arriving car can directly drive to the space in front of the window. And the next is, how long is an arriving customer expected to wait before starting the service? Now let us solve this problem, and we have been given the arrival rate here, which is 10 cars per hour, and the service time is given as 5 minutes. So 5 minutes for one car, and we will convert it as, for 1 hour we have 60 minutes, so 60 minutes per hour divided by 5 minutes per car, and it will come as 12 cars per hour. So here lambda is 10 cars per hour, mu is 12 cars per hour, and we need to make sure that the unit of time in both lambda and mu should be same. Now let us solve the part 1 first. It says that what is the probability that an arriving car can directly drive to the space in front of the window. So the probability of an arriving car can directly drive to the space in front of the windows is given by P0 plus P1 plus P2. Now what is this? Let us understand this. So the arriving car can come and directly capture the space in front of the window is possible when there are 0 customers in the system, or 1 customer in the system, or 2 customers in the system. Because if the customers are 0, 1 and 2, there still be an empty space outside the window for car. So these three probabilities are possible for a car that can directly drive into the space in front of the window. So the total sum of these three probabilities is equal to the probability that an arriving car can directly drive into the space in front of the window. So let us find these. So the value of P0, P1 and P2 can be given as, P0 is 1 minus lambda by mu, and P1 is given by lambda by mu multiplied by 1 minus lambda by mu, and P2 is given by lambda by mu whole square multiplied by 1 minus lambda by mu. Now we have lambda as 10 cars per hour, mu as 12 cars per hour, so we will put these value in this equation, and so these are the values here. We have put these values. Now let us see what is the result. So P0 is coming as 0.166. Here value of P1 is coming as 0.138, and the value of P2 is coming as 0.115, and the total sum of these probabilities is equal to 0.419, or we can say that 41.9%. So there is 41.9% probability that an arriving car can directly drive to the space in front of the window. Now let us move to the second part here, part B, and it says that how long is an arriving customer expected to wait before starting the service. So it has been saying about the waiting time of the customer, and it says that before starting the service, that means it is asking the waiting time in the queue. So it is represented by WQ, and we know that WQ is equal to LQ by lambda. And when we put the value of LQ in terms of lambda and mu, we will get this equation, which is lambda by mu multiplied by mu minus lambda. Now let us put the values of lambda and mu in this equation. So this is the value, and it is equivalent to 10 by 24, and which is equal to 0.416 hours, or we can 55 minutes. So the waiting time, or we can say the average waiting time in the queue, is given as 25 minutes. Now let us move to another question. The question here says that a branch of Punjab National Bank has only one typist. Since the typing work varies in length, the mean service rate 8 letters per hour. The letters arrive at a rate of 5 per hour during the entire 8 hours workday. if the typewriter is valued as rupees 1.50 per hour, determine first the equipment utilization, second is the percent time that an arriving letter has to wait, third is the average system time, and the last is the average cost due to waiting on the part of typewriter, that is the idle time cost. So let us solve this, and we have given the arrival rate here, which is lambda, and it is given as 5 letters per hour. So letters are arriving at the rate of 5 letters per hour, and the service rate is given as 8 letters per hour, and we have the work day of 8 hours in a day, and the typewriter is valued as rupees 1.50 per hour. So let us solve the first part here, part A, and it has asked the equipment utilization. So we have learned that the utilization factor, which is represented by rho, is given as lambda by mu. So let us put the value of lambda and mu here, and it is coming as 0.625. So this is the equipment utilization, or we can say utilization factor. Now let us move to part B here. It says that the percent time that an arriving letter has to wait. So the percent time an arriving letter has to wait is equal to the probability that the server is busy. So probability that the server is busy is also known as the utilization factor, which shows that the amount of time the server is utilized, and it is represented by rho, which is equal to lambda by mu. So let us calculate this. So in previous part A also we have calculated this, and if we represent this in the form of percent, it is 62.5%. So the probability that the server is busy is 62.5%, or we can say that 62.5% of time an arriving letter has to wait. Now let us move to part C here, and it says that determine the average system time. So it has been asked the average time that a customer or a letter spends in the system. It is represented by WS, and it is given by 1 by mu minus lambda. So let us put the value of mu and lambda here. So we'll got here 0.33 hours, or we can say 20 minutes. So the average time that a letter spent in the system is 20 minutes. Now let us move to the last part, part D, and it says that the average cost due to waiting on the part of typewriter, that is the idle time cost. So here the idle time cost of the typewriter per day, it is calculated by, first is when the working hours per day. So we know that it is a 8-hour work day, so this will be 8. Now fraction of idle time, this shows that the fraction of time in which the server is idle, and we know that server is idle when there is 0% in the system. So we need to find P0 here, which is the probability of having 0% in the system, and multiply by the cost of idle time per hour. So we need to calculate the cost of the typewriter in this idle time. So let us find this. So the working hours per day is 8, and the value of P0 is given by 1 minus rho, and we have calculated that rho is equals to 0.625. So this is P0 multiplied by the cost of typewriter here. So cost of typewriter is 1.50 per hour. Now when we calculate this, we'll get the value as rupees 4.50 per day. So this is the idle time cost of the typewriter per day. So I hope this lecture is useful to you. If you like this, please subscribe and share. Have a nice day. Thank you.